Swayam Prabha. Digital India. Educated India.
Okay, so we will continue the discussion on definition of various types of emissivity. So we started with the spectral directional emissivity yesterday, then it is epsilon lambda dash, right. So the lambda denotes that it is a spectral quantity and the dash denotes that it is a directional quantity. So two directions are involved, the zenith angle and the azimuthal angle, so namely theta and phi respectively, and lambda refers to the spectral, refers to the fact that it is spectral. So we started integrating one by one. So if you integrate with respect to direction, then it is called hemispherical. So you got hemispherical spectral quantity, but if you integrate with respect to wavelength and leave the direction, it is called the directional total emissivity. Now we will do both the integrations, so we will finally get the hemispherical total emissivity where the integrations with respect to wavelength as well as theta and phi are done. So this is denoted by so it should be a function of temperature. Please note that the final emissivity will be a function of temperature, okay. However, sometimes this dependence is weak, so you say that the emissivity is independent of the temperature, right. Now this epsilon of T is given by the emissive power of a real surface at a given temperature T divided by the emissive power of a black body at the same temperature. So what is the equation number? 18, good. So we will erase this. Okay, so what is this ET? Correct. Epsilon lambda dash multiplies by IB lambda into sin theta cos theta d theta d phi d lambda, okay. Therefore okay, because the denominator is 1 by sigma t to the power of 4. Okay. Now this is equation number 20. It is a very important relationship because if you are given the spectral directional emissivity epsilon lambda dash, it is possible for you to accomplish the 3 integrations and get the epsilon, okay. For a gray diffuse body, or gray diffuse surface or body, epsilon lambda dash is not a function of either lambda, theta or phi. Therefore, epsilon lambda dash can be taken out of all the three integrals, correct, and integral triple integral IB lambda cos theta sin theta d theta d phi d lambda is given by what is that finally? Sigma t to the power of 4, that was the Stefan Boltzmann's law, right? If you pull out the epsilon lambda dash and accomplish the triple integral, you will get sigma t to the power of 4. Therefore, for a gray diffuse surface, so if somebody gives you the spectral directional emissivity, that is the hemispherical total emissivity for a gray diffuse surface. Okay. So if you look at a bird's eye view, so this is integration with respect to theta phi. Correct. So if you have the spectral, so we can write the symbols also. What is this? People are not able to see that. Correct? This gives you a bird's eye view of the various emissivities involved. Okay. Fine. So now let's solve some problems. Problem number 6. It is going on. So arrow mark means it continuously goes as 0.1 up to infinity, right? Epsilon lambda, it does not stop with beyond 2 micrometer, it is having a uniform value, a constant value of 0.1, right. Please take down this problem. The hemispherical spectral emissivity of tungsten, the hemispherical spectral emissivity of tungsten The hemispherical spectral emissivity of tungsten is given below. The hemispherical spectral emissivity of tungsten is given on the blackboard. Consider a cylindrical tungsten filament. Consider a cylindrical tungsten filament that has a diameter of d equal to 0.8 millimeter and length equal to 20 millimeter. Consider a cylindrical tungsten filament that has a diameter of d equal to 0.8 and length equal to 20 millimeter, full stop. The filament is enclosed in an evacuated bulb. The filament is enclosed in an evacuated bulb. The filament is enclosed in an evacuated bulb and is heated by an electrical current. The filament is enclosed in an evacuated bulb and is heated by an electrical current. The filament is enclosed in an evacuated bulb and is heated by an electrical current to a steady state temperature of 3000 Kelvin. To a steady state temperature of 3000 Kelvin. A. Determine the total hemispherical emissivity. Determine the total hemispherical emissivity when the filament temperature is 3000 Kelvin. Determine the total hemispherical emissivity when the filament temperature is 3000 Kelvin. B. Assuming that the surroundings are at 300 Kelvin. Assuming that the surroundings are at 300 Kelvin. Assuming that the surroundings are at 300 Kelvin. What is the initial rate of cooling? Assuming that the surroundings are at 300 Kelvin, what is the initial rate of cooling of the filament? Assuming the surroundings are at 300 Kelvin, what is the initial rate of cooling of the filament when the current is switched off? The tungsten properties are given below. So there are two parts to the problem. The first part is just using your fundas of various definitions of emissivity and figuring out the hemispherical total emissivity. The second is actually a heat transfer problem where using this emissivity, using a knowledge of heat transfer, you will write the governing equation and get the initial rate of cooling. I will help you with the second part, but first part you should be able to do. First part, the first few steps involve the conversion of hemispherical spectral emissivity to hemispherical total emissivity. Some steps are missing because whatever I have done in today's class, I gave you a formula to convert epsilon lambda dash to epsilon. From that you have to go to one more step, you should be able to convert epsilon lambda to epsilon, correct? Are you getting the point? The first step is very simple. Given a distribution like this, how will you get the epsilon? Is it right? It is not area under the curve. Please note it is not area under the curve because there is a f of 0 to lambda will come. Okay? You derive it first 5 minutes, do not look at me, try to do it yourself. Anyway, I am going to do it on the blackboard. Yeah, start. Okay, so let us look at the Is correct? The first thing we did this morning. Now I also know this. What is the relationship between epsilon lambda and epsilon lambda dash? 1 by pi into cos theta sin theta d theta. That IB lambda doesn't come, right? I doesn't come, okay. All of you please look at the blackboard. Epsilon lambda dash into cos theta sin theta d theta d phi, right? Correct? Yeah? Okay. Now it gives you some idea. Have you taken this? I'll clean this up. You are able to get these arguments? Look, I didn't do any magic, I am just shuffling, I mean just keeping certain terms ahead of the integral and certain terms I am pushing it after the integral. Now I know this is pi times epsilon lambda, okay. What is pi times IB lambda? Huh? EB lambda, okay. I did two things. I absorbed the pi and put it EB lambda. Denominator I can interchangeably use EBT or sigma t to the power 4. Okay. Now we have to apply it to this case. Vishwas, what's the problem? No system. Emissivity is on the surface. No, emissivity surface. Okay. What? Who? We are always looking at surface properties. That will decide the cooling rate. But we are just evaluating properties. Geometry doesn't come at all. There is a surface with spectral directional characteristics. Know how to characterize the surface first. The other stories will come. Geometry will come. But we have not even come to that stage. First you get epsilon, then you talk about other stories. There is so much drama in converting it to epsilon itself. Okay, it is very important that you realize that so many things are there. Simply a layman, a man in the street will say epsilon sigma t to the power of 4 is radiation. It's not so easy, you see, we are struggling. So many fundas are involved, correct? It's very rigorous. Okay. Now what is the story? Now epsilon for the tungsten, can I say 0 to 2? Is that right? Because it has got only two values, epsilon 1, epsilon 2. Okay. Suppose I want to pain you in the exam, I can give, each time you have to stop and then go back to a function chart and then get the emissivities. Now what is epsilon 1 for this problem? Very good. What is epsilon 2? Okay. Now is epsilon 1 constant over 0 to 2? Yeah. Can you pull it out? Yeah. Is epsilon 2 constant from 2 to infinity? We can pull it out. But what is this fellow 0 to 2 EB lambda divided by EBT? That's where I will come again. What is 0 to 2? EB lambda divided by EB of t, that is f of 0 to lambda. I mean 0 to 2, that is f of lambda 1 lambda 2. The second fellow is 2 to infinity, means 2 to infinity, that is lambda 2 is infinity. Now that you know what is the temperature, 3000 Kelvin, lambda 1 you know, lambda 2 you know, get the f function, use the f function charge, first get the emissivity of the tungsten. 5 minutes, please do it. Is everybody through with this? First get the emissivity of tungsten. Okay. Yes, 0.358, right? Okay, so how much is this? That's all, huh? No. No. So it's just 0 to lambda 1, right? There is only one thing, right? Okay. Correct? Now 7377. Point 358. Okay. So, is this surface a grey surface or a non-grey surface? Grey means epsilon lambda is independent of lambda. It is a non-grey surface. So in today's class you have learned how to get the hemispherical total emissivity if the spectral emissivity is given for a non-grey surface. So you know how to handle a non-grey surface now. If it is completely jagged and all that, you have to do the integration. It will become you have to integrate with respect to Planck's function, you have to write a MATLAB code. Otherwise, if it is nice variation like this, then you can use the F function chart and quickly get the answer. Now let us go to the second part of the problem. So I have given epsilon of T. Therefore, if the temperature changes, please watch, if the temperature changes, even though this epsilon lambda remains the same with respect to lambda, if the same tungsten filament were to be at 2000 Kelvin, this lambda 1 T will become 4000 micrometer Kelvin. Therefore, the epsilon T will change. Therefore, epsilon in general is a function of temperature. But sometimes it is because 0 to 2 is such a small, 0 to 2 micrometer is such a small portion of the total electromagnetic spectrum, and for the remainder of the spectrum it is only 0.1. Remainder of the spectrum it is 0.1. You can actually calculate that for various temperatures, after a certain range of temperature, epsilon will become more or less equal to 0.1. Because from 2 micrometer to infinity, it is 0.1. Are you getting the point? Fine. Now, we want to calculate the initial cooling rate. Okay. So we have to get an energy equation for this. We can assume that the whole tungsten filament is at the same temperature. Okay. And we can also assume that convection heat losses are negligible. Therefore, because now no information is available, correct, when it starts cooling, the temperature is 3273 Kelvin, 3000 Kelvin. Surroundings are at 300 Kelvin. We have just calculated the emissivity. We know the Stefan Boltzmann constant. You know the surface area. I have given you the density and you know the volume. Calculate the M, you have the specific heat. So we will get the initial cooling rate. When the current is switched off, what is the cooling rate will follow. But this cooling rate will not remain constant because right side it is a function of temperature. As soon as it cools, the temperature will fall. Cooling rate will further fall. So that is why it is called a non-linear function, because the cooling rate is the rate of change of temperature. The rate of change of temperature is itself a function of the temperature. So that is why it is a non-linear function. Yeah, please calculate the volume. From the volume multiplied by density, get the mass, and then substitute, get the area. You should have the lateral surface area and the top and bottom area also. Do all that and please get the initial cooling rate.
The T power 4 part is emissivity of tungsten, that's okay. But T infinity comes from the sides of the walls, right?
From the surrounding.
Surrounding. So how do you know that that is also epsilon?
No, this formula you have to assume it as, you take it as granted. After 1 month I will derive this formula. This I assume that you have learnt in basic heat transfer course, I am assuming. Okay, how to formally, when we formally derived IB lambda, we will formally derive this also. Okay, but you just wait. Now take it as granted and then proceed. See, his question was why did he put the T infinity within that epsilon and all that. Okay, this will become clear after I come to the concept of radiosity. Now you can write a MATLAB code for this and find out, because emissivity will also change with temperature, right. So the cooling rate will keep on changing, so you have to write a code and okay, then done. Done. Okay, let's do that. What's the mass? So what is the volume? Amrita, what is the volume? 2.00? Is it correct? 1 into 10 power?
Minus 8.
Minus 3.
8.
Volume? Exactly 1. Okay. So A. What is A? 2 pi RH. What is the funda here? 2 pi RH plus 2 pi R square mean? 2 pi RH pi R square pi R square. Bottom, top, side. Yeah, what is A? Five point 10 to the power of minus. What is M? Yeah, we can do this. Huh? Yeah.
Minus 387.15.
Not 387, some 1000 will come, man. Minus 3000? Don't be carried away. Don't be under the impression that in 1 Kelvin it will lose 3276 and become minus 276. Huh? This is the initial cooling rate. Within a few microseconds, the cooling rate is so heavy, temperature will go down, epsilon will go down, and it will reach saner values. Got it? So, this is how you solve problems involving epsilon. Now, there are other properties like reflection, transmission, absorption and all that. Each of these may have a variation with respect to lambda. You need to characterize all this, and then your energy equation may not be so simple. There may be combined conduction and convection, then you have to handle this. Now, the energy equation may be such that you have to solve the Navier-Stokes equation, or you may have to solve the Laplace equation, Poisson equation, then you have to add radiation to it, then it becomes a totally what is called a multi-mode or combined heat transfer problem. The analysis becomes difficult. Nowadays in Fluent, radiation modules are available. In fact, I believe the latest Fluent has an optimization module also. So some basic optimization can be done, okay. So the basic CFD software now also have a good radiation module, so you can add radiation, because radiation is a passive means of enhancing the heat transfer, okay. Now we have another 7 minutes, we will solve a quick problem, a small problem, and then we will get back to, we will take some other substance like zirconia at 3000 Kelvin, which has a different epsilon lambda versus lambda characteristic, and compare a zirconia filament with a tungsten filament and find out what are the energy requirements, what are the emissivity, and how much of energy is available in the visible part of the spectrum, so that we can compare for engineering purposes which is a better filament. But no, filament itself is gone, okay. CFL also going, okay. So I think LED has come. CFL now they say that increases cancer risk, something, no. Even mobile phone, there was a study yesterday, too much of leads to brain tumor and okay. Problem 7. The directional total emissivity of non-metallic materials, the directional total emissivity of non-metallic materials, the directional total emissivity of non-metallic materials may be approximated as epsilon theta equal to epsilon n cos theta, where epsilon n is the normal emissivity. Okay, given by epsilon n cos theta, where epsilon n is the normal emissivity. What does it mean? When theta equal to 0, cos 0 equal to 1. So corresponding to 0 angle, zenith angle, it is like this. It is the maximum value, that is epsilon n. Show that the total hemispherical emissivity for such materials is 2/3 of the normal emissivity. Show that the total hemispherical emissivity for such materials is 2/3 of the normal emissivity. It is a quick one. I wanted to give you a flavor of one problem in lambda variation, one problem in theta variation. We will get back to this filament problem of zirconia filament. It will take about 20 minutes. We will do that in the next class. So from now on, some definition of absorptivity, then lots of problems, reflectivity problems. You will get back to my regular format of other courses where lecture problem, lecture. Okay, we did lot of theory in the first 2-3 weeks. Now theory and problems will be intertwined. Okay, what is epsilon? IB lambda, va? Yeah, IB lambda divided by why? Yeah, but anyway it is not coming. I can have you done the integration with respect to lambda?
This expression we have not done.
Huh?
This expression we have not tried.
No. That is not. No. I given you directional total, so I can put it as IB, right? Huh? Correct? Okay. Anyway, that I am going to pull out. IB can be taken out. Okay. What is epsilon theta? denominator is pi, huh? Yeah, I did so many things. I did one integration with respect to azimuthal angle. I pulled out 2 pi in the numerator. Denominator, the total solid angle is pi. I kept the denominator as pi. Then for epsilon cos theta, epsilon I pulled out of the integral. Cos theta into cos theta, I got cos square theta, right? So, yeah, I quickly did some steps. All these, you know. I changed the variable from theta to cos theta. Therefore, 0 to pi by 2 I changed. There was a minus sign. Okay. Then again I changed from 1 to 0. Okay. Now, cos cube, this is so if you tell me the normal emissivity, I can give you the total. What is the emissivity? I can give you the directional total emissivity. If you give me the directional total emissivity, I can give you the total hemispherical emissivity. Okay, it's 2/3 of the. But epsilon n is king. He is the highest. It is like this. Okay, so we will stop here.